Hello everyone. So today let's discuss the topic modular inverse algorithm, right? So previously we had discussed the modular exponentiation algorithm. Now we'll be going with the modular inverse algorithm. Yeah. So basically we have discussed about the Euclidean algorithm and the extended Euclidean algorithm. So we will be making use of the extended Euclidean algorithm within the modular inverse algorithm. While discussing the extended Euclidean algorithm itself, I have said that we will be making use of the so this is very important. This you have to know because the same thing will be making use of it within the modular inverse algo. We have come to the topic, this one, modular inverse algorithm now. Yeah, let's see what the definition states here first. Yep. So a modular inverse of a modulo m is the number x such that a into x mod m is always equivalent to the 1. Yep. Simple. Yeah. A modular inverse of a modulo m is a number x such that a into x modulo m is equivalent to the 1. It exists if GCD of a comma m is equivalent to the 1. It exists if GCD of a comma m, this one is equivalent to the m, right? So that is a and m are co-prime, right? So a and m are co-prime, right? So for the prime m, we cannot compute it quickly with the exponentiation, right? Using the this one Fermat's little theorem, right? So for prime m, we cannot compute it quickly with the exponentiation using Fermat's little theorem, right? So let's see what we can do here. Let's come to the explanation part here, right? So the modular inverse x here, the modular inverse x here satisfies a into x equals 1. A into x equals 1, right? Mod m basically, right? So if GCD of a comma m, if it is not equal to 1 accordingly with the definition, see here, no inverse exists. So it exists if and only if GCD of a comma m is equivalent to 1. See, if GCD of a comma m is not equivalent to the 1, no inverse exists because a shares a common factor with the m, and we cannot get 1 as a linear combination. We cannot get 1 as a linear combination, right? So let's go with the two common algorithms, man. One is extended Euclidean algorithm, right? So one is extended Euclidean algorithm, nothing but double EA. Extended Euclidean algorithm, we have already discussed this one. So I'll just click this one. So let me go to the Python one. So yeah, this one, we have already discussed this one, right? So this is the Euclidean algorithm. Where is extended Euclidean? Sorry, this one actually. Yep. So it's the extension to the this one Euclidean algorithm, right? So we have already discussed this one. If you don't know, you can just go through the video and then come. Yeah. So here, see, we can just go with this one. What do we call? So extended Euclidean algorithm. So basically, it finds the integers x comma y such that a into x plus a to the power of x plus m into y. Sorry, a into x plus m into y is equivalent to the GCD of a comma m. Right? If GCD value, if it is equivalent to the 1, x mod m is the inverse, right? Works for any m here. They strictly mentioned here, right? So this is fine. So we need to know the Fermat's little theorem as well. Whenever we are going with a modular, this one inverse, so we will be going with a that small return something that will be going with the Fermat's little theorem, right? If you would have solved the this one modular inverse, some the problem. So if you would have used the modular inverse within the some problem, actually some problems it might be based on the complete number theory problems, right? So you'll get the opportunity to go with this one modular inverse or the modular exponentiation within the code forces or the code shift quite often, even the coder, right? So if you're doing CP, many times you get the opportunity to implement this one. If you would have made use of the modular inverse, so that small this one helper method you will write, and you'll be mentioning based on the Fermat's little theorem, this and that, right? So we will be making use of the Fermat's little theorem, right? So what does the Fermat's little theorem say here? States here actually, if m is prime, if m is prime, then inverse is a to the power of m minus 2, right? So just remember this. This is important. If m is prime, suppose m is prime, then inverse is a to the power of m minus 2 mod m, right? A to the power of m minus 2 mod m. So this is fast with the modular exponentiation. This is fast with the modular exponentiation, right? Extended Euclidean algorithm is general and safe for the non-prime modulus. It is only safe for the non-prime modulus. Yeah. So formats method is faster when modulo is prime. When modulo is actually prime, right? So usually we'll be going with a formats method, right? Most of the times, yeah. We'll get the opportunity. As I've said, if you're doing CP, you would have implemented this one many times, right? Usually the last three or the last four questions, usually the question might pop up actually, right? Based on the number theory, you will get many opportunity to implement the same thing. Yep. So let's continue with the same. So now the exact same thing, whatever we have discussed in the explanation part, let's try to implement the same, or let's try to articulate the same thing in the form of code. Yep. Now let's start writing the algorithm, or let's start writing the code first. Yep. Let's go with this one, extended Euclidean algorithm. As I've said, we'll be making use of the extended Euclidean algorithm within the modular inverse algorithm, right? So basically, it returns g x comma y with a into x plus b into y, that is equivalent to the g, that g is equivalent to the gcd of a comma b. We know this one from the explanation part. Let's write the function. You'll come to know. I'll just give here def. So I'll just go with the extended GCD. So this is fine. Let me pass the parameters here, a comma b. I can copy paste the same thing, but it's fine. Let's write this one. Let me type this one so that I don't forget. Yeah. So if we are comparing here, comparison operator, if it is equivalent to the zero, then let me go with the return. Very recently we have implemented the extended Euclidean algorithm, right? So this one will be a comma 1 comma 0, right? This is fine. Next, let's go with a recursive step, in the sense we need to compute, or we are computing the GCD and coefficients for b comma a modulo b, right? So this one, g comma x1 comma y1 equals. So let's recurse here. Let me copy the function name here, extended GCD. So extended GCD of what, b comma a modulo b, a modulo b. So this is fine. Yeah, now let's do one thing. Let's update the coefficients to match the original a comma b, right? So x, let me assign this one to the x1, and also y, let me assign to the x1 minus. So this one will be a by b, this one a by b into y1 into y1. So this is fine. Finally, let's do one thing. Let's return g comma x comma y, g comma x comma y. Yep. Now let's do one thing. Let's move on with the further things here. So let's go with a modular inverse using the extended Euclidean algorithm. So this works for any modulus m. So I'll just give here def. Let me go with the mod inverse here. Mod inverse. So I'll just go with the extended Euclidean algorithm. So this is fine. A comma m. So this is also fine. Yep. So within this helper method, I'll just go with g comma x here, g comma x. So let me consider one more thing. I'll just consider this one underscore method. Yep. So this is equivalent to extended GCD of this one, a comma m. So what is this basically? We have written in this way, g comma x comma this one underscore is equivalent to the this one extended GCD of a comma y, m actually. So see, we are finding the GCD and coefficient x such that a into x plus m into y is always equivalent to the g, right? So that's what we are doing here, right? So this is fine. Next, let's do one thing. What if g is not equal to 1? What if g is not equal to 1? Then let's return none. Yeah, let's return none. Yep. So we are going with the inverse, basically, which doesn't exist when GCD not equal to 1, right? So this is fine. None, capital N. So this is fine. And one more thing, x may be negative. Yeah, x may be negative. Let's reduce the modulo m to get the positive representative. Meaning, so let me return here x modulo m. Let me return x modulo m. So this is fine. So the next step would be here, modular inverse using the format's little theorem, only valid when m is prime, right? So I'll just go with the def mod inverse. So this one I'll just go with a format. So this uses a format little theorem, right? So this is fine. A comma m here. So power with three arguments does fast modular exponentiation in Python. Always remember this point. The just remember this one, POW, this one power with 3 arguments actually. So we had used this one in this one modular exponentiation as well, POW of A1, X1, X2 or something like that we used, right? So first one is nothing but the integer, next the power value, next the mod value we use. These 3 things. POW with the 3 arguments does fast modular exponentiation in Python. Always remember this. Inverse is nothing but a to the power of m minus 2 mod m when m is prime. When m is prime. So we are considering inverse. Inverse is a to the power of m minus 2 mod m when m is prime. So see, I'll just give here a return. I'll just give here return POW. So this one will be a comma m minus 2. So this is fine. Also m. Yep. So this is fine. Yep. So the next part would be here. Let's go with the demo. Let's go with the demo examples and printing output. So I'll just go with the def. Let's do one thing. So this is it for the actually theorem. Sorry, not the theorem. This is it for the algorithm basically. Yeah. So we just made use of the this one, right? Formats little theorem here. So uh, it came to my mouth. Right. Sorry. This is fine. Now let's go with the demo examples and printing output. Yeah. So I'll just take this one from the Google man. So this is it for the algo basically. Yep. So I'll just come here. Let me paste this one. Yeah. So this is demo. See, examples, we are going with the co-prime, prime modulus, inverse exists. Should be, answer should be 4 here, right? And for the 10, 17, we are just going with the co-prime, prime modulus, inverse exists actually, and it should be 12 here in this case, right? So we are considering when GCD not equal to 1. Here, inverse doesn't exist at all, right? So we have discussed this one already. Yep. Within the explanation part as well as writing the algorithm. Yep. So for a comma m in example, so we are just printing the example a equals a and m modulo this one m actually. Yet inverse 1 equals, we are just calling modulo inverse double EA, meaning extended Euclidean algorithm, this function. Yep. So this is fine. If inverse this one, if inverse 1 is none, then we are printing Euclidean extended Euclidean algorithm, no modular inverse when GCD not equal to 1. Else we are going with this one, right? So for you, we will be making use of the formats little theorem only when modulus is prime, right? Here we demonstrate when it's safe, right? So here we are just demonstrating when it is safe actually, right? So modular inverse format. So this is just the function that we have used here. This is fine. We are just going with format modular inverse, inverse 2. Oh, so we are going with this one actually, a into inverse 2 modular m. This is fine. Else this one print. If it is not prime, then skipped, right? Modulus is not prime. Only will be making use of the formats little theorem only when modulus is prime. Just remember this one. This is very important, right? So this is extremely important, right? So we are going with a prime print statement. This is fine. Next, we are going with a simple this one deterministic for the small m, meaning primality check for the demo purposes, right? So we are just going with is probability, sorry, is probably prime, right? So if n equals to 2, so this one we know, man, prime numbers, calculating prime. So if n is less than 2, obviously false. If n modulo 2 is 0, meaning remainder, if it then it will be even number, then basically we'll return n equals to 2. Then when r equals 3, r initially we are keeping this one 3, then we are going with r into r less than or equal to n modulo this one equals 0, then we are returning false actually. Yeah, remainder shouldn't be 0. R equals r plus 2. So then we will return true, else we will be returning true. So this is fine, man. Yep. Now, the output that we need to get here. So we are well versed with the algorithm. Yeah, we have discussed the algorithm step by step. I hope we have no doubt within the algorithm, right? So now let's discuss the this one. What do we call examples that we have considered? First, we are going with the 3, 11, 10, 17, and 6, 9. For the example a equals 3 and m equals 11, basically modular inverse is 4, right? So we are checking one here. Modular inverse should be 4, right? And format modular inverse in the format extended Euclidean algorithm also we have to get 4, and formats little theorem, that one also should give us this one, modular inverse equals 4, right? So this is fine for the first example. For the second example, same thing, a equals 10 and m equals 17 here, modular inverse is 12 here, and with the formats little theorem, then also modular inverse equals 12. So because it is prime, right? So this is fine. M is prime. M is 11, M is 17 here, both are prime, right? So here then we are going with A equals 6, M equals 9. Here 9 is not prime number, right? So 9 is divisible by 3 actually. Yep. So 9 is not prime number here. So A equals 6, M equals 9. So extended Euclidean algorithm, nothing but EEA we are printing, I think. So this one, we have to get this one. EEA, no modular inverse because GCD not equivalent to the 1 here in this case. Yeah, GCD not equivalent to the 1. And format, in the format we are skipping here. This one we have to get format skipped because modulus not prime here for the third one, for the third one that we have considered, right? So now we have the idea. Now we have the idea. Let's do one thing. Let me completely copy this one. What do we call a file name? So I'll just give Control J, Python followed by the file name dot py. Yeah. So we have name y is not defined. Did you mean y1? Where is this actually? Line number 27. So return g comma x comma y we are going with, right? So what's wrong here? 1 second. So this is fine. Oh, here again, x1. So x, we are assigning this to the y1 actually. This is fine. This has to be actually y1. This has to be y1. Now this is fine. Y we are assigning to the x1 minus a divided by b into y1. Yep. So this one we know, extended Euclidean algorithm. So now we have to get the correct output, I believe, if everything goes well. Yeah, you can clearly see here. Example A3 M11 for the first example that we have considered here. 1 second. Yeah, this one A3 M11 here. So M is prime here. So modular inverse is nothing but the 4. Yes, this is fine. Check one. And formats by formats little theorem. So modular inverse is 4 itself. Yep. So this is fine. A formats little theorem. Go with the format only when the modulus is prime, right? So A is 10 and M we have 17 here. 17 is prime. M is prime. So modular inverse is 12 here. So this is fine. With the help of extended Euclidean algorithm. Also, with the help of formats little theorem, this one we have the prime number, right? Prime modular actually value. So modular inverse is 12. This is fine. Next, we are going with A equals 6 and M equals 9. No modular inverse, GCD not equal to 1. And format skipped modulus not prime. Yeah, we have discussed this one and we are getting absolutely this one, absolute correct output, right? So meaning we are getting the desired output here, right? So this is fine. Yep. So we are done with the this one modular inverse algorithm. Yep. So as we are done with the modular inverse algorithm, let's do one thing. Let me summarize whatever we have learned so far. Yeah. So let's move on with the first point here. Modular inverse x, what it does, it satisfies a into x. It satisfies a into x modulo m equals 1. Modulo m equals 1. Yeah. So it exists only when GCD of a comma m, GCD of a comma m. So let me write it over here, exists only when a GCD of a comma 1 equals 1, meaning the value. We are comparing this one actually. If the value is equivalent to the 1, right? So this is very important part. So this is the main part actually, right? Again, let me tell you, modular inverse x satisfies a into x modulo m equals 1. It exists only when GCD of a comma m is 1. Yep. So we can just make use of extended Euclidean algorithm. Extended Euclidean algorithm for general reliable method. It works for any modulus. Yeah. So the third one here, we can make use of the formats little theorem as well. Yeah. We can just make use of the formats little theorem. Yeah. Formats little theorem in the sense we can just go with power with the three, this one, what do we call, three values actually. We can just go within the Python or followed by a, x, y, any. So three values will be going with. So this is the integer value. This is the to the power of whatever we give that value, exponentiation value in the sense, this one integer value, exponentiation value, modulo value, right? So we can just make use of the formats little theorem. Usually we'll be going with, so a m minus 2 as well as m. Usually this one we represent this one in the this one, what do we call, in the formats little theorem. So we'll write like this, m minus 2 and m, right? So this is fine when m is prime. It's fast and convenient, right? Also the last point here is always check the GCD first when you aren't certain M is prime. When we aren't certain that M is prime, always check the GCD first. Yep, it has to be equivalent to the 1, right? So, yep, this is the this is it about the modular inverse algorithm. Yeah, pretty simple one. Pretty simple one if you understand. If you don't understand, everything will be difficult itself. This is fine. Now we are done with the modular inverse algorithm. Yeah. Next, we'll be discussing on the topic Chinese remainder theorem as well as the Euler's totient function. Yeah. For now, this is it. Thanks for watching, guys.